Hello, I'm Mohammad Reza Timori, a mechanical engineer, and welcome to the Mechanical Engineer Essential channel. In part 9 of our ANSYS Fluent tutorial series, we begin our second project, focusing on the simulation of a vertical axis wind turbine, VAWT. This type of turbine features vertically oriented blades, and in our CFD model, we analyze a horizontal plane cut through the 4 vertical blades to better understand the aerodynamic behavior. In this project, we will explore 2 common solution strategies used when there are moving parts in the simulation domain. Both methods will be demonstrated using the same model, allowing us to compare performance and accuracy. On the right side of the video, you can watch how the turbine works and see the blade rotation in action, giving you a visual understanding of the motion we're about to simulate. Stay tuned as we guide you step by step through the simulation of this fascinating renewable energy system and learn powerful CFD techniques in ANSYS Fluent. In this project, we are going to simulate the rotation of a vertical axis wind turbine, VAWT, using 2 different approaches available in ANSYS Fluent, each suited for different levels of accuracy and computational cost. In the first part, we will simulate the rotating blades using the MRF, moving reference frame, approach. This method allows us to simulate rotational effects without actually moving the mesh. It treats the rotating zone as if it's in a rotating frame of reference, which makes it computationally faster and suitable for steady-state problems. It is ideal when we are interested in time-averaged flow fields and not the detailed transient behavior. Use case: good for quick assessments and average performance of rotating machinery. In the second part, we solve the same model using a transient approach where the mesh actually moves over time. This is done using the sliding mesh technique, which is more accurate as it captures the unsteady interaction between rotating and stationary parts of the domain. Although it is computationally more expensive, it gives us a detailed look into time-dependent effects such as vortex shedding, periodic forces, and dynamic blade interactions. Use case: ideal for detailed flow analysis, noise prediction, or performance fluctuations. Now that we've introduced the project and discussed the simulation goals, let's jump into the software and begin setting up the model. First, open ANSYS Workbench from the Components Systems section on the left panel. Drag the Fluent module into the project schematic area. Rename the system to something meaningful, like Moving Reference Frame, to help us keep track of the simulation strategy we'll use in this part. Next, double-click on Setup to begin configuring the simulation environment. In the Setup options, make sure to select 2D as our simulation type, and also enable double precision for improved numerical accuracy. We'll leave the other settings at their default values for now. Let's proceed to the next step and start building our CFD model. Now that we've set up the Fluent environment, let's move on to importing the mesh and preparing it for simulation. Once Fluent starts, go to the File menu and click on Import Mesh. Select the mesh file named ws5simpleWindTurbine.msh and click OK to load it into the solver. After importing the mesh, it's always good practice to check the mesh scaling. Navigate to Problem Setup General and click on Scale. Here you can confirm that the blades have a radius of 1 meter from the origin, 0, 0, and the outer bounding box spans plus or minus 5 meters in all directions. Next, we need to check the mesh quality. You can do this in 2 ways: go to the Mesh menu and select Check, or from Problem Setup General, click on Check. Note, the mesh check will fail, but don't worry, this is expected. The reason is that this mesh contains intentional non-conformal interfaces. That means the mesh nodes do not match perfectly across some boundaries. This setup is necessary for simulating motion later in this workshop. To ensure proper fluid flow across these boundaries, the solver needs to interpolate between the mismatched mesh sections. In general, whenever you create multiple parts in Design Modeler, you'll often have non-conformal meshes. That's why we need to explicitly define the interfaces in the next steps to make sure Fluent knows how to handle them properly. Let's move forward and take care of that setup now. Now that we've checked the mesh and confirmed the presence of non-conformal interfaces, it's time to create the mesh interfaces so that Fluent can correctly handle the fluid flow between these disconnected mesh zones. Let's do this step by step. Go to the top menu and navigate to Problem Setup Mesh Interfaces, then click Create/Edit. Now you'll see a table where we need to define each mesh interface. For each row, do the following. Enter a name for the mesh interface in the first column. This helps identify the interface easily later. For example, we might call it Interface 1 or Blade Interface. In the second column, click on the name of Interface Zone 1. This is one side of the mesh interface, for example, the rotating zone or a blade face. In the third column, click on the name of Interface Zone 2. This is the other side of the interface, typically the stationary zone or surrounding fluid domain. After filling in the details, click Create to finalize that mesh interface. Because the mesh nodes do not match perfectly across these zones, Fluent needs this interface pairing to properly interpolate data like pressure, velocity, and temperature between the two sides. This ensures that the simulation remains physically accurate even though the mesh is not conformal. You'll also notice a visual gap between the two zones when zoomed in. That's normal. This is exactly what these mesh interfaces are designed to handle. Now that the interfaces are defined, go back to the General tab, and click Check again under the Problem Setup section. This time, the mesh check should pass successfully. That means everything is correctly connected and ready for the next stage of our simulation. Now that our mesh and interfaces are ready, let's configure the physics models we'll use for this simulation. Go to Problem Setup General Solver. Ensure the pressure-based solver is selected. The steady state option should remain active. Since this is part 1 of our project, using the moving reference frame (MRF) method, we're simulating a rotating system and a steady frame of reference. A steady state approach is faster and sufficient for this analysis. Now we define how the simulation handles turbulence. Go to Problem Setup Models Viscous, then double-click. In the dialog box that opens, choose K-2 under the model type. Then, under K-Epsilon Model, select Realizable. Leave all other settings at their default values. Why K-Epsilon Realizable? The K-Epsilon model is a widely used and robust turbulence model, especially for rotating flows like wind turbines. The realizable variant improves accuracy for swirling and separated flows, ideal for turbine simulations. Now let's check the working fluid. Go to Problem Setup Materials. By default, the material air is already selected. We'll keep it as is. Density, 1.225 kilograms per cubic meter. Viscosity, 1.7894 times 10 kg/ms. Why keep defaults? These are the standard properties of air at sea level and room temperature, and they're perfectly suitable for this wind turbine simulation. Next, we assign physical properties to each part of the geometry. Go to Problem Setup Cell Zone Conditions. In the list of zones, select Fluid Outer Domain and click Edit. In the dialog box, you'll see that air is already selected as the material. No motion needs to be defined for this zone. Simply click OK. The outer domain represents the stationary part of the simulation. Since it doesn't rotate or move, we don't need to assign any motion to it. It acts as the background or free stream region where the airflow enters and interacts with the rotating blades. Now, let's set up the motion for the rotating region, the core where the turbine blades are located. Go to Problem Setup Cell Zone Conditions, select Fluid Rotating Core and click Edit. In the dialog box, just like before, the material air is already selected. Now, check the box Frame Motion to activate the Moving Reference Frame (MRF) model. This tells ANSYS Fluent that this zone is rotating rather than stationary. Keep the rotational axis origin at its default value, 0, 0, since the turbine rotates around the origin. For rotational velocity, enter 4 radian per second, which defines the angular speed of the turbine. Finally, click OK. By enabling frame motion here, we are simulating the effect of a rotating turbine without physically deforming the mesh. This approach is faster and simpler than dynamic mesh motion and is ideal for steady-state simulations like this one. Even though we're using a steady-state solver, we can still account for the motion of rotating parts, like our turbine blades, thanks to a method called the moving reference frame, MRF. When we define the rotation of the core, Fluent doesn't actually move the mesh. Instead, it adds a source term to the governing equations inside the rotating zone. This extra term accounts for the local acceleration caused by rotation. This approach simulates the effects of rotation, such as centrifugal and Coriolis forces, without the need to move the mesh. That's why it's ideal for situations where the geometry is symmetric and the rotation is continuous and uniform. So, by simply specifying the rotational velocity, we let Fluent calculate all those effects in the background accurately and efficiently. We've reached the end of this part. In this session, we successfully began our second ANSYS Fluent project focused on simulating a vertical axis wind turbine, VAWT. We opened the workbench and set up the project using Fluent. Imported the mesh and understood its non-conformal nature. Created mesh interfaces to allow fluid interaction across the rotating and stationary zones. Set up the solver using the pressure-based, steady-state method. Enabled the K-epsilon turbulence model. Finally, we applied the moving reference frame, MRF, technique to simulate the core's rotation at 4 radian per second, all within a steady-state solution. If you found this helpful, don't forget to like the video and follow the Mechanical Engineer Essential channel for more practical and exciting CFD tutorials. In the next part, we'll continue with the simulation setup and move closer to seeing the turbine in action.